Please keep all your electronic devices sectional. Please keep all your electronic devices sectionals. Okay, so please write down your name and student ID. This is also the same as your assignment. A lot of your assignment didn't write your name and student ID. Please write it. Make the exercise so that we can identify you with your work. And make sure you write down your name and student ID. Also, this quiz too, because there's so many quiz. I don't know which quiz you are answering. Right? So you need to write down which one if you're. Okay? So this treating particular always write your assignment quiz. Okay, so you can start. What is pro? Yeah, pro. That's good. I think I told you the shape of a real number before. Just draw. I give you 10 minutes. Okay. I mean drawing, yeah. So I give you 10 minutes and 12, 16. And then draw yourself. And how is that? Draw. So for question 2, I give you the hint. So make sure you find the n epsilon for me. Okay. So if you draw the real number, you should explain like what's complete, what's the order.
Can explain now.
I mean like that picture should sort of explain. You don't need to write down. Is that I'm giving you hint how to think about this. 要看他，你看他就是看他表演，就越画越兴奋，给他计划，给他计划。对不起。然后要看他越做越兴奋，给他。Okay, I think I draw real number in this class a lot. I told you to bring some ruler to the class, right? It's very important. And this related to part 2. Hello? Hello? Done? That's I'm there. Okay. Maybe 3 more minutes. Peter. Okay. Maybe Chun Xian. Chun Xian. Chun Xian. Can you help collect from the back? And then we shuffle the paper and then give to the front. And then maybe Yushen. Is it Yushen? Yushen. Yushen. Can you collect from the front? And then you shuffle to the back. Okay. And then I think both of you will meet halfway. So
这边 number 如果默写全部那三个 exam 可以给100分。
等下我们讨论。等下我们讨论。等下我们讨论。Yeah, so try advocate for your solution. I mean, no, for the quiz paper that you mark. Okay, so try see if you can help that person to get some marks on. Okay. Try advocate for the quiz that you mark. Okay. 有点像，这个看来有点像，微博给他的，我练的肯定是好好。OK，你给他2张，你给他2张，他有每个人有2张。
因为我两个公主的意思是价别嘛。
哦，是哈，会不会你后来 check 到他没有拿？Okay, try advocate for the quiz paper you mark. If you can get some marks from him or her. Okay, done. You got who haven't got it. So please mark using what? Using different color, and then try not to use red ink. Okay. Try use different color, and then try not to use red ink. You can use pencil actually. You can use pencil. Okay, so draw the real numbers. I think before drawing real numbers, I draw something like this in the notes, right? Did you remember? Or anyone reading the lecture lesson? And I read the lecture notes or not? Like I draw something like this. When they add up, they become 0. Anyone see this picture? If no, I suggest you go and see. No, I never see a GG or then. No one's reading my lecture note. What? No. You shouldn't just read the previous one. You should read the current one because the current one have update. And then the previously got problems, I will update there. You see? You didn't read my lecture notes. Then how? So how gonna teach now? If you don't read my lecture notes? The previous one is just for your reference. I mean, like I will update it. Right. Okay, maybe I show you here. I think it's in lecture 4. No one read this so sad. I draw it out, no one read. No one read lecture 4. Not yet. I haven't said the answer yet. I just say, did anyone read this? You want see this? No. Got some of you got. Some of you got. Yeah, you 不懂又不问哦，很奇怪哦，不懂又不问哦。我不是花爽哦。In whatever I say in this class, I draw in this class, don't treat it trivial. I'll test you one. Okay, so please,
The main one is a real number greater than the natural number greater than the integer greater than the natural number. I thought the main point is this one.
No, I got picture. I draw for fun. I'm not for fun. Everything I do here is not for fun, okay? So please read my lecture notes. Okay, but then this is not the full picture yet, right? The full picture is you need to put in the completeness condition, right? And then the order condition actually, okay? So the order is the, actually, did I comment here? Maybe I didn't comment. Okay, so I remark here, this tripolynomial actually define a total order. Did you know the total order from this one, right? Actually, something is a total order, you can put it in a chain. Put it in a chain. Okay. So after the chain, so what do you get? You get a complete field. So the density things, right? Every real number have every two real numbers there's a rational, and then every.
This density,
No, I did. What do you mean? I did do in class. I did prove in class about the density. I think it's in the same room here. It's this room. I proved the density as well. Yeah, I proved this.
Oh.
Right. I have a lemma did in class, right, as well. Then Xi Yang asked why square root 2f plus m over n is irrational, right? Okay. So together, this dot will form a chain first. Okay, form a line. Form a line, yeah. But this line actually, okay, so this is the real number line you see, right, in your high school, real number line. Okay, so if any person draw a line like this, also acceptable. Okay, as long as it's a line, because I can compare which one is toward the left, toward the right. I can compare. As long as it's line, we give full marks. Okay, good. Good. Okay, good. Okay, everyone agree, Okay, how about B? Then this will kind of answer B already. Okay, so B S1, how should you draw it? So you have a number line, right? And then you have all the A that's squeezed between T. So you have T and minus T like that, right? So this point is the origin point. And then all the points here should be excluding minus T to T and then everything here. This is S1, right? Okay. How about S2? Again, it's the same setup, but then the way you choose your A is different already, right? So you need to choose everything away from T, greater than T or less than minus T. Okay, so this is a two picture. So each picture is like 1.5. This is the picture I draw in class as well, right? Did I draw this? Yeah, I drew this in class, right? Okay, yeah, I drew this in class. Okay, so make sure you pay attention in class. Okay, any questions so far for this? No? Okay, agree? Agree, good. Okay. 那边有人摇头 ，OK 了，有 OK 啊？ You don't understand. Don't understand. You okay? Okay. So there's a subtlety here. I want a strict, one I don't put strict. So see whether you want to take T or minus T or not. So if they miss that that point here, maybe deduct 0.5
他做晒的
多少
啊，
We'll see how it goes.
应该是错了，错了。
Okay. How about the next one? Okay, this one is a very current thing, right? Yeah, very current thing. So how should we pick this n epsilon? Greater than n. Okay. So let's start with the hint. So let epsilon greater than 0. So actually by Archimedean property, we can find n in n such that 1 over epsilon is which way around? 1 over n is smaller than epsilon, like that. Okay, so maybe we can test whether this n will work or not. Okay, let's check this n if this n works. So pick n epsilon to be n. Okay, so that for all n greater or equal to n epsilon, but we care about 1 over n plus 1, absolute value of 1 over n plus 1, right? But then this is always positive. Okay, so I can throw away the absolute value first. Okay. But then this is n plus 1, or this is n. Okay. So what we had here was 1 over n less than or equals to 1 over n epsilon, which is equal to 1 over n, which is equal to epsilon, right? But then is there a connection between these two? Connection, I can go here. What? Huh?
Just not big enough.
Sorry?
I'm just not.
Oh, you just noting. Okay, sure. So what's the, you say smaller than equal to?
I just set the
Ah,
small n smaller than n plus 1. It's smaller or greater, I forget already. I just
and
Smaller or greater?
No. Yeah, n plus 1 greater than n.
sure, n plus 1 is greater than n, right? Confirm, right? Plus 1 ma.
Yeah.
Okay. So here, what's the connection I can put here? So if you invert it, become less than, no? So that you can combine everything together. Okay. Make sense here? Okay. Maybe people can give different choice depend on how they write. Okay, but then the n that 1 over n will go for 1 over n plus 1. Okay, this is the part. Okay. Good. Okay, so you can give your marks and then sign your name and then give back to me.
That's what I want to tell you.
错
到完了，
看
下一份。
看一下姐。
跟你看，我是要讲去看。
Okay.
Once again.
你帮我收下。Okay, sign your name. Calculate your marks and then sign your name. Yes.
因为其他 immediate property 要怎么我是可以调的。我们来直接 one over n 直接上跟 n plus one 应该是，就没有其他 immediate property 就直接
没有，你要n 的话需要这个。你要 exist 那个 n 的话需要那个 Archimedean property。会够一点分。 Okay, everyone, got it. 一般人算一下有没有工人，一个人那边。是26啊，算这个26分，这个26分。Okay. So what do you feel? 啊？greater smaller 看错 ，OK。
第二题还好。
OK， B to 0。
以前我是默写那个 build 给那个 x
那个是那
好，那就我查了。反正就这样3分里面是不 OK。
OK。How about the rest? What do you feel? 25单，25个人还是26个？
在里面
没有，那个不是，那个是 job 的。到人我们有钱。something wrong. How about the others? OK 吗？难不难？难很难。小难，大的难是吧？大的都高。OK 好。So I mean like so the point of this quiz is to help you to keep up revision. So what is the main point you miss? Okay, so these points are very important. Okay, to understand the course aspect. Understand? Okay, because this quiz is actually considering very little portion of your grade, but then it's very important to remind you what to learn, what to keep up with. Okay, does it make sense? Make sense? Okay, so whatever you don't understand in class, right, in lectures, right, you should always keep to date or ask me if you don't understand. Okay, make sure you ask. Okay. And then what else? Oh, another thing. Hey, actually, I found out on Monday that kind of a problem. How many of you need to go to integrity class? Only 4, 5 actually. Chung Shen also is it? Monday class. Integrity. Okay. So do you have to like miss all the replacer class? Because actually we have 1 tutorial and 2 lectures, right? Yeah. So middle ground is it possible like 1 hour, 1 hour? Is it possible? What do you think? Not possible. 13呢？那个老师会怎样很凶？他没有管不是？为什么不会念？你没有啊？你跟他讲我有 valid reason。哦，你想上 integrity，OK， 这样没有办法，这样没有办法，OK， 这样没有办法。OK， 你可以去 integrity。
可是你是有 record。
呀，我有 recording。对，因为上次我们讨论时间的时候，我只记录到你们是讲 before 3 PM 嘛，就 regard to before 3 PM 都有，然后不知道你们早上有没有课。
你问我们这个新
对呀，所以如果你不讲的话，我就不知道。But then 现在只有4个人，我觉得还 manageable， 5个人啊 maybe。But then if 如果整个 class 的话，就要再改，要 calling 骂我的一个 class。对啊，就你这样子做了狗就这样子改了。So in that case 就 tutorial 至少来 OK 一天吧，可以商量一下。tutorial 我需要 presentation 的。我们 replacement 没有办法，你讲其他班太多时间的。lecture 我可以给你记吧，反正 tutorial 就是下个白夜了，可以吗？ email 一下，你们就 group email、bulk email CC 我也可以，你 CC 我啊。如果真的怕的话，你 CC 我啊。你讲班上拍多少时间？你还去 call presentation。如果你怕的话，你可以 CC 我，你们就一起 email 啊，不要一个一个一起。然后你们要的话可以 CC 我。Okay. So you want to take a break first, or you want to start the break? Break. Okay. Maybe break for 5 minutes. Okay. 12. We start 12:45, and then you can sign in your attendance. 真的咩 Okay. Break 10 minutes. Okay. Hi. You can sign in your attendance. 我在 course info 那边有写，
就是它不是每个
就是图咯，
有个单
图。你拿你的 course info 出来，你拿你的 course info 出来。Yes. 啊，对，没有错。我希望我会算，我会算，我应该会算，这样。对，等下次最好告诉我你们什么时候有课啦，因为不然的话有点麻烦。因为现在又是电子嘛，平时的话我直接勾就好。因为刚刚这个区不是当时
这个现象，我还是最
哦，是从这边
这个是这样，是那时候我们
对，还是不能塞。
可以的，我不知道为什么突然有
哦
生出来，
因为之后我一点，因为上次是那个系统有问题，然后我没有 online
哦，所以我现在在学的是3个拜4拜5了，我都没有听到。
对，拜五那天，对，拜五那天拜一忘记那个 group 忘记没有叫你们参与的哦。因为拜五，对，我后来之后会办人。
好的，
首先请下跟你请一下，现在我在星期一，OK，因为我在那，回去放假，合适。
刚才那把为什么我就这样子写罢了？OK，这个没关系，我现在就这样子写罢了，就是因为我提到 Archimedes problem，就这样子写不了，就是照它上来，就是我看那个 Fitzpatrick 的答案也是这样，就是考试的时候要这样子写的，还是
要，我班上也是这样，
就是 Archimedes property
用
and
就是
然后再
每个理由都要写出来，每个理由都要写出来。为什么会有那个东西？那个理由要写出来。我班上也是这样做，对不对？每个理由啊，每个理由。make sense。对，没有错，少了一个例子。对，谢谢。lecture 几？对，开播这 lecture 几啊？OK，好，谢谢。Yes。
3 over third n plus 2 over n plus 3这种也是要写，就是它就是这样写，就是
对。怎么
也是要写
写什么？你要写什么？
immediate problem。
没有啦，你知道为什么要用到 Archimedes
我懂，就是因为它这个比较简单，还要考的，就是这样。
不是，你要知道那个 Archimedes property 是什么来的？
就是要就是比如就是比如你有一个 你懂那个 n 是 natural number 嘛？然后你那个 e over，比如你有 e over 什么啦，它是一个 real number 嘛？你的那个 natural number 大过 real number，你才可以换那个，就是猜这个 in 猜
不是换，它是 exist 那个，
啊，就是
当你要找那个 n 的时候，你
把
就需要到那个 accumulate
这种就是这种，
看你要不要找咯，我不知道要不要找。如果要的话就要咯，不要就不用。有什么意思？
这个是肯定要的，因为
肯定要的，你就要把它写成那个 form 咯，你要写成这个 accumulate 的 form，那这个 form 长这样，
就像你刚写的嘛，
嗯，这个长这样，这个其实是它的 corollary 的，but then 它其实就是 accumulate property 了，就是这个，除非你有这个 epsilon 在这边，然后你有一个 n 要在上面这样子，
哦，
这个 n 的存在
我懂，就是你不可以直接 e over n epsilon 直接丢下去，就
也可以啦，反正这个 equivalent 我们会嘛，只是 real number 嘛，but then accumulate 是给你这个 natural number，如果你要这个 natural number，你就要 accumulate。
可是我就看到 v 呢，我说 pro，
我们还有另外一个 form，
还有一个问题，
什么问题？
有没有什么纯 algebra 的方法 prove sub 那个 free group 的 subgroup 也是 free digit？
为什么不是去抓？
你把它定 proof 的方法是 common space，
肯定有啊，肯定有吧？没有咩？
把它
有吗？
把它定 proof 的方法就是回答那个就
没有咩？
space，但是它不会有 algebra 的方法。
你上网找看，好像确实那个是一个问题啊，这样
啊，
就是你问的那个题目，
它显然不是，而且它可能会有更多的 generator 出来。
有点像那个什么那个叫什么那叫什么东西？sub module 的情况。
哦，
这个不要
啊，我有 upload 一个 assignment 啊，几时到期啊？assignment two 啊，几时到期啊？忘记了。这个班总共有几个 assignment？4个不是？4个，OK。我这个班，
好，
权威有顺 Helen、洪俊、有顺、思慧、天乐、齐阳、品杰、刘昌浩然、恒玉 not here right？李成玉，yeah。百涵呢？董百涵，I think I saw him。华月，诶，李成玉 here 的话，I don't remember which one。哦，成玉 is you，OK，good。恒玉 I think not here。钟汉、玉汉、钟贤、凯德、魏杰、俊威、子晴、文伟、抗毅、一兴、林一兴，OK，对，新阳、红杰。Yeah，哎，your attendance got problem or not? No, some of you got problem. I will manually update them later when the system get better. 怎么起啊？这样啊？
有叫名字
啊？
有叫名字
没有啊？你怎么睡觉？睡觉累？ Okay, shall we start? Let's start. Okay, so next we'll discuss about nested interval theorem. Any idea what nested means? Nested. Nest.
define a Python function
Python go use nest.
you use a function, you refer the function itself inside a Python function.
So function in function.
Yeah.
Yes. I guess so nest is like containing a bird, right? So we are nesting something. Okay. So for every n in n, let I subscript I be the closed bounded interval. Okay, in real. Okay, closed bounded is very important in this case here. Okay, closed bounded. In future, you will learn this as a compact set. Okay, but we won't do compactness here.
Interval, bounded interval.
Even closed interval, bounded interval. Yes, but bounded doesn't mean close.
Yeah.
Yeah. Okay. So close mean bounded. Let me see. Okay, in this case is in this case is. In this case, yes, that's right. Okay, suppose that an plus 1 is in an or n. Okay, so okay, you see nested here. You see nested here. So again, right, draw the picture, right? Draw the picture. So what is interval? How to draw an interval? You should have two endpoints, right? A and bn. Okay, and then an plus 1, bn plus 1 is something inside here. Okay, nested, and then go into like that. Make sure you know how to draw these things. Okay, for n, and the length, okay, the length of bn minus an of in should converges to 0. Okay, so this is what I draw in the picture here. So getting very small, very shorter and shorter and shorter and shorter. Then there exists a unique point x in R such that this x here is in in for every n in. Okay, not that just here just say converges to 0, converges to 0. And then you will find one point in every closed interval here.
Your A and BN are not equal, right?
A and BN are not.
And then BN is smaller than BN, right?
Sorry, yeah. If they are equal, I think there's no contradiction.
They are equal to singletons alone.
Yes, that's right. So that unique point is that singleton.
No, I'm B, you mean not B.
Sure. Sure. Should I edit here? I think maybe I should add here. That non-empty. Okay. Everyone okay? Can you imagine? Okay, so at this point, does this interval get until you convert to 0? Actually, it's 10 points. So how on earth do we prove this? So in this proof, right, there are two parts to do, right? One is existent, one is uniqueness. Okay, so there are two things to do here. You need to prove the existence, and then you need to prove the uniqueness. Exist and unique. Right. So let's prove existence first. Okay, so first of all, let's write down what we had. So we had in plus 1 is in in. Okay, so what does this mean here? So if I draw it out, actually you can see the endpoint will look something like this, right? Okay, the endpoint an plus 1, bn plus 1 will squeeze in between an and bn. Okay. But at the same time, what did you see? When the subscript n increases, an actually increasing or non-increasing actually because this is not straight. Okay. But for bn it is non-increasing. Basically non-increasing. So it follows that an is a non-decreasing sequence, and then bn is a non-increasing sequence. Okay. Okay. So what do we learn yesterday? Monotone, very good. Okay, so if we have a monotone sequence, then that one is the definition of but what's the theorem? Monotone. Yes, what's that?
If the end is
Non-increasing.
and bounded above, then it is.
Then it converges, right? Okay. So is it bounded above?
Yes, by Bn.
Okay. Or actually by B1 actually, right? By the first term here. Okay. So furthermore, an is less than equals to bn for all n, but then at the same time, you have the largest term, right? B1. 1, 2, 3, 4, 5, 6, 7. Okay. So actually it is bounded above. An is bounded above. So if it is non-decreasing, going up and bounded above, it means what? It means that it converges. Good. So therefore, an converges to something, let's say A. Therefore, sum A. By monotone convergence theorem. Okay. So similarly, you can do for Bn. Bn is non-increasing, but then it's bounded below by A1. Okay, so also converges. Converges to something. Okay, so similarly, Bn converges to some B, let's say. Okay, for some limit B. Okay. Actually, we can show that actually these 2 points is the same. Actually, they converge to the same point by a trick. Okay, this trick is kind of important. I think you saw it before already. So note that we can write Bn as An plus Bn minus An. Like that. Okay. So, so what? So these two side converges, right? So Bn converges. Okay, An converges. Bn minus An, what happens? You still remember? This length will converge to 0. Okay, so this term converge to 0. This term converge to A. This term converge to B. Okay, so if you take limit, B equals to limit of n to infinity of Bn equals to the limit of these two things. And then by limit law, we can split it out, right? Okay, by limit law, we can split it up because we know the convergence of An. We also know the convergence of Bn minus An. Okay, so one of them is A, the other one is 0. Okay, so A equals B. Actually, these 2 points the same. What else we need to do? We need to make sure that this point live inside A and IN for all n, right? Okay, we got a point and then we need to make sure that it live inside IN. So how to show that? Wait. So you want to show that something is living inside IN, right? So what does it mean by living inside the interval IN? Let's say this one is A and B. What does this mean? What this phrase means? X is in here. What's the definition? I think I draw the picture for you, right? In the quiz. What does this mean? You got an interval AN, BN. Your X is living inside this range here. So it means what? It has to satisfy X greater or equals to AN and X less than or equals to BN. Okay, so you need to show this. Okay, this is what you need to show it live inside a table. Okay. Right. So we need to establish the inequality. Okay, so how to establish the inequality? So note that A actually live inside IN. Okay, for ON. Why? Because all the IN should be less than or equal to A. Why? A is established as a supremum. Okay. But then at the same time, though, this A is equal to B, right? But how do you find B? B actually is defined as the infimum. Okay. Infimum, the greatest lower bound. Okay, so this is less than Bn. Okay, so it satisfies this inequality. Make sense? Okay, good. Any questions so far? Question? Feel free to ask. I won't score you. Yeah. If you have a question, feel free to ask. Good. Okay. Then we can continue. So, how about uniqueness? Okay, how about uniqueness? So, meaning what? We assume there are two differences. Okay, very good. So instead of doing that, we just look at every other X that's living in AN, BN for every N. Every X that live in this interval for every N. Will you get confused if I write like this? You confused? Okay, I look for every X okay, that live in AN, BN for every N.
I'll write them for N at the front.
For ON at the front.
For N, for X.
Let me think for ON.
Because X depends on N.
Because X is dependent on N. X shouldn't depend on N.
X should depend on
I want to pick something that is in.
because X depends on A and B and A and both A and B depends on N. So X depends on N.
X shouldn't depend on N. Because I want to true. I want this element of to be true for all N. So X has to live in A1, B1, A2, B2, A3, B3, A4, B4. It's the same X.
If that's the case, then you can put intersect.
Intersect, yes.
Symbol.
Yeah, right. Yeah, that's right. That's right. Yeah, that's right. So this is actually the shorthand notation. So let me think. So you prefer this, is it? So I think you prefer this. Yeah.
For all X.
I think we can keep it like this. This one I happy. I think you also happy.
Unless you question the meaning of intersect, yeah.
Okay. Everyone okay with this one? We can live in all A and B. Everyone okay with this? So you live in A1, B1, live in A2, B2. Okay, so then we have, what do we have here? I mean, we just write down what we had. X should be greater or equals to an because it's the left endpoint for all n. But then this implies what? This x actually is the upper bound, right? Upper bound for an. But then you have least upper bound, right? So this x should be greater or equal to your least upper bound. Okay. But then at the same time, okay, on the other hand, we also have x less than equal to bn, okay, for all n, because it's on bn is on the right endpoint. Okay, so it means what? This is a x smaller than everything. So x is a lower bound. But then you have the greatest lower bound just now, right? So this implies that x actually is less than or equals to the infimum of bn such that n is in n. But then this thing is b. But then we just proved that b is equal to a. So you have a greater than equal to x, x greater than equal to b, a. So this means what? So hence we have x equals to a. So that. Does it make sense? Okay. Okay. So maybe I give you an examples why this closed bounded condition is very important. So for example, if you pick the open bounded one, it doesn't work, but still nested. Okay, but this one doesn't work. Okay, can you see that this distance here will go to 0? I think we just proved in the quiz, one of them will go to 0. And then nested for sure becomes smaller because you can get larger. And then why won't work?
It's on this side. Because it's upper bound. This upper bound need when they try to
Actually, not really,
but
but least upper bound just need bounded above, right? Huh?
minus
It-
one
it's
minus one over.
Sorry.
If you want it to not work, you can pick one minus one and one over n.
Minus one.
Actually, very simple one. Suppose that you have 0.1 over n, and then you take an epsilon from it, and then you by the one property, you have the 1 over n less than epsilon for potential number n.
Mhm.
And then you can and then you have the open interval from 0.1 over n, and then epsilon is not inside.
And then
Yeah, so this is for any arbitrary natural number n, and for any arbitrary epsilon inside this in, you can find a 1 over n this kind of thing, and then construct a new interval, and that thing is not inside. Maximum for
not inside. What you
the epsilon is not inside.
No, what I mean is you won't be able to find a point. Yeah, we won't be able to find a point or a unique point that lives in every in. Yeah, so the claim is this. Okay, so you can try and prove this, but then I put inside the notes. So this is my claim. So there doesn't exist an unique point. X in in. In for all. Okay, so this is the claim. So maybe you can prove by contradiction. Suppose there is one. Suppose there is one, and then you can continue from there. Yeah, I think it's what Qiang commented, I guess. Yeah, actually, it's basically contradicting the Archimedean property. Okay, you can try and show this. Okay. Right. The point is the limit point is not in there, and the limit point is. I haven't defined you what's the limit point. I guess at some point I would tell you what's the limit point is. Okay. Any questions so far? No. Okay. So this is a very good exercise. I try to do this. This is a good exercise on applying Archimedean property. Applying, how to spell like this. Archimedean property. Okay. So next, let's do a squeeze theorem. So this is a squeeze theorem for sequence. Okay. So to squeeze it, suppose you have 3 sequences such that there exists some capital N in N, where for all n greater than n, small n greater than capital N, Bn is squeezed in between An and Cn. That is. And moreover, where is the squeezing part? So actually, we need An and Cn to converge. Converge to the same point. Okay, otherwise it's not as squeezed as possible. Okay, so we want to squeeze it to a limit L. Then we will know that Bn have to converge to L also. Okay, so there are 2 parts here. Bn converges and then converges. Okay, 2 parts here. Do you know what this picture looks like? Can you imagine this picture here? Sandwich. Okay, so squeeze, yes. So what do you mean by squeeze? Maybe squeeze from above, squeeze from bottom. Okay, but then well, so let them squeeze a bit more. So squeeze to a limit, let's say to 0. Say to 0. It doesn't matter what happened before. As long as there's some n, okay, it started to get squeezed. We'll say that this Bn here will squeeze to the same limit, converge to the same. That makes sense. Okay, so I think up to this week, you realize that for sequence, right, we don't really care about the finitely many term at the front. We just care what we call maybe the tail of this sufficiently large, the tail. Tail, everyone can get the idea. Tail, we buy. Right. So how are we going to show this? How are we going to show this? Well, there's limited condition, right? So you just write down what this means. An converges to L, what does it mean? Cn converges to L, what does it mean? Just write it down. And then write down what you need to do to show that Bn converges to L. Just write everything down. And then you see you can put things together. Okay, so let's write down the proof. So maybe I present this proof a little bit different. But then it's the same thing we talked before. So again, fix epsilon greater than 0, right? So then assumption, there should exist n1 epsilon and m2 epsilon such that n greater or equal to n1 epsilon implies that absolute value of an minus L is less than epsilon, and n greater equals to n, when n greater equals to n2 epsilon, we have Cn converges as well. Okay, so now what we're going to do here, pick the max. Pick the max. Pick the max. How many max you need to pick among how many number? 2. Is it enough to prove the Bn? You say to be n1 and 2, yeah. How many? So at least n1 and 2 you need to consider, right? Okay, because you want to make sure that both of these converges. Then, yeah, actually there's this when do you get the speed? The this. Okay. So let's see why we need this. Let's see why we need this. Let me input here first. I will show you why we need it. So in this case, we will have this big inequality here. So first of all, I can squeeze my Bn in between An and Cn first. Okay, so this one is making sure by the capital N. And then, I can make sure that my Cn is bounded above by L plus epsilon. Okay, so this is controlled by who? Or C1. Okay, maybe I rewrite this. So this one is if and only if Cn minus L plus epsilon greater than minus epsilon. This one is An minus L less than epsilon greater than epsilon. Okay, so this is controlled by N2. Okay, but on the other hand, I can bound my An by what? L minus epsilon. So this is controlled by N1. Okay. So if you combine all this inequality together, what do you get? Dn is squeezed between L plus epsilon and L minus epsilon, which implies what? Which implies Bn minus L is squeezed in between epsilon and minus epsilon, which means the absolute value of Bn minus L is less than epsilon. Okay. Good. Question? Any question? Okay, so actually we only use one side of the conversion. Use one side. Okay, but then we really need these three M here because one is controlling the convergence of An, the other one controlling the convergence of Cn. The last one control the inequality between A and C. Okay, good. Question? Question? Any question? 有点小安静，听得懂我在讲什么吗？不懂讲问是吗？会吗？会觉得不懂讲问吗 ？maybe 我们休息一下。小安静。然后对吗？后面 maybe 文伟啊，是不是现在文伟吗？还是叫你陈伟？陈伟啊，陈伟觉得怎么样？啊，会也骗我啊，不会就不会，会就会啊。OK 啊 ，OK， 好啊，什么？再讲一次啊，这个天乐老师上线了，他现在讲一次。啊，
今天是陈伟老师上线的
啊，可以讲一次吗？不能讲一次的话，就代表不会哦。所以你要用这个来测量你能会不会。Okay, so to make sure you know or not right, try to explain the things to your friend or to yourself again. Okay, 因为你会觉得说，我觉得我会啊，其实你不会，很长的时候。So make sure that you can explain things to your friend or to yourself again. Maybe without looking at the notes. Okay, 用这个来测量你到底会还是不会。所以on my point of like 又要拿你来玩，没有看不看？就是说like but for me when I say mathematics can how to say explain this work, it's like sometimes we need quantification. So we need to quantify like the quality, for example. Quantify, for example, this is how I say, what is the level of understanding? How do you quantify it? How do you check it? Okay. So what okay?
就是听课的时候是 existential， 复习的时候是 that exists， 考试的时候是 for all， 会出来的时候是 negation， 就是算了，因为这边
Okay, I'm kind of 知道还要讲什么 but then yeah. 我大概知道了，yeah，对，很好。
真的吗？要剪进下你讲的。
哦，简历在我才懂啊。但是就是讲学的懂一点点，然后读的时候要读全部啊，
啊，
然后出来的时候什么都不会这样。
哦，
Yeah, something like that. Something along that line. Yeah, maybe. Yeah. Okay. So, this is one way to test your understanding. Okay. Because 不然的话，你等下考试又不会写，又不会写在那边，对不对？就很奇怪，你讲你会，反正你又不会。And so there's one way to do it. So that's why I really encourage you to go study to discuss maths together. Very good. Yeah. Or you make your own study group. Also okay.
study. Yeah, we are planning studying group.
Very good. That one is very good.
Also include academic groups. This one group.
Okay. Chiang is a talking job here. Okay. So what time? 1:30. Okay, good. Okay, so in this case, so let's try this. So maybe give you a hint that this sequence will converge. Maybe try and see how is it converging. Nobita. No. No Nobita, no ratio test, no single compress test, whatever test. Huh? Whatever test. I taught that course before, so no those tests. So whatever I just introduced you the squeeze theorem, right? You should think about squeeze theorem. Yeah, you should think about squeeze theorem. How to squeeze it. 死的要用这个答。Let's try squeeze with what's the thing you need to look for? Squeeze between two sequences such that the two sequences will convert to the same thing. Okay, so you need to look for this thing. Well, maybe I can give you a hint. So a hint is what? You don't need, never mind, you don't need to speak. People need hints. Okay, maybe use this hint here. This hint is very useful. But will we prove it at some point? Okay. Now is a it's a bug here. We haven't defined what is sine for you, but then after we introduce differentiation, we will introduce what's the sine function. We will define it using audit group. All right, for now you can use this hint. Okay, so if you look at this sequence here, right, there are two parts you need to control. Right? Okay, there are two parts you need to control. So let's discuss one by one. So for the numerator, right, what's the largest possible number? N plus one. N plus.
Yeah.
Right, this one can go as large as one, right? Sine. Yeah, N plus one. And then the smaller one.
N plus N minus 1, is it correct?
And
yeah. N minus 1,
right? Okay, because this sine can go minus one. How about this one? The denominator. What's the largest possible? N plus 3. The smallest?
N plus 1.
N plus 1, yes. 2 minus 1. This one. Okay. So meaning what? Meaning this an here actually is bounded by n plus 1 over the over n plus 1. Okay, it's the smallest one. And then bounded below by n minus 1 over n plus 3. Okay. So on one side you have a constant function 1, but on the other side also converge to 1. How do you show it?
1 minus 4 over n.
So we can rewrite this as 1 plus minus, okay, minus 4 over n plus 3. Plus 3. Okay, good. So in this case here, this is a constant function sequence, right? This convert to 1. But then this one, you should be able to show that convert to 0. Okay, very similar trick we play in the quiz. Right, this one. I think you need epsilon over 4. I think epsilon over 4 should be 8. Okay, epsilon over 4. Yeah, try and show this. Try and show this converge to 0. So in this case here, our an will converge to 1 by squeeze theorem. Okay, so far. So far, okay. Okay. Question? Any question? Any question? So above you have sequence bound converge to 1, below you. Okay. Okay, let's continue. So next, we're going to define a function to be increasing. I think we had this before, right? We define what is non-decreasing, right? So maybe I remind you what is increasing. So for all xy in n such that x less than y, we would have jx less than jy, strictly less than. Okay. So next we're going to define something called a subsequence, not subgroup, subsequence. Okay, so we're going to use increasing function to define subsequence. So a subsequence of an is any sequence obtained by omitting some term of your an. Okay, so this is very English, right? You throw away some term inside of an, but then more mathematically we can write like this. Okay, so if of an, yeah, right. Okay, so this one of an, that is if there exists an increasing function okay, j from n to n such that dn equals to ajn. Okay, so maybe these definitions looks very long. So let's write down some examples. So let's look at this example here. An equals to 1 over n. Okay, so what's the sequence here looks like? 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, or 7, like that. Okay. So can you give me a subsequence? Can you give me a subsequence? 1 over 2, 1 over 3, 1 over 5.
1 over 1, 1, 4, 5, 1, 4.
Okay, maybe you can stop here first. So what do you mean by subsequence here? Then these will rename it, become B1, B2, B3, and then maybe B4 here. But then originally, what are they? They are actually A2, A3, A5, and then maybe A115. Okay, does it make sense? Okay, so did you see the increasing function here? Do you see increasing function here? I send 2 to 1, 3 to 2, 5 to 3. Wait, no, sorry. I send 1 to 2, 2 to 3, yeah, and then 3 to 5, and then 4 to 115. And then what does it mean by increasing? If in the domain you have x less than y, you also make sure that your jx less than jy. So can you see that actually 2 is less than 3, 3 is less than 5, 5 is less than 4. So you cannot pick the same number. You cannot pick 1/5 again. Or you go to here and then you pick the one at the front. Okay, you should continue the sequence. Does that make sense? Okay. Yeah, you cannot pick your, so meaning you cannot pick your B4 here. You also cannot pick your B4 here. So you cannot do that. Okay, it must be increasing. Make sense? Okay. Good. So next question. So proposition. If a sequence converges, then every subsequence must converge to the same limit. To the same limit. Okay. Can you think about this for a while? If you have a sequence converges, okay, so maybe think of a convergence sequence. Okay, converge to some point. If you pick up any subsequence, it should converge to the same limit. Agree? Do you agree? You agree? Okay, if you agree, then we have to show it. Okay, so let's show it. So let's prove. So let's give the name of our subsequence AJN, for example, okay, to be a subsequence of AN. So what's our goal here? You know what's our goal? We want to show that for epsilon greater than 0, there exists some n epsilon in n such that for all n greater or equals to n epsilon, the absolute value of a jn minus L should be less than epsilon, like that. Okay. So what should we do here? We know AN converges, so there's one assumption we can use. Okay, so suppose AN converges. Well, so let epsilon greater than 0 again. Then let's say we just pick this n based on this convergence. Okay, so there is a positive integer n such that is small n greater than n, we will have an minus L less than. So, okay. So is it possible to use this n as our n epsilon? Okay, so maybe we just choose first and then we test it. Does it working? So now take n epsilon equals to n. We take n epsilon equals to n. Well, if n greater equals to n epsilon, which is n, actually, what does this mean? Actually, this implies that actually Jn should be greater or equals to Jn here, because this is an increasing property. J increasing property J. But then we actually get Jn greater or equals to n as well, actually. Why? This actually require a little proof. Okay, so actually this is a lame. Yeah. Maybe we can think about why this is true. Maybe we can think about why is this true. For example, you can think about where is J1. What one can go? Where one can go? I've been there. Where one can go?
Sequence, not subsequent.
No. So this J is a function from n to n, right?
Yeah.
So where the number one can go. No, not about that. Okay, so what's J? You still remember what is J here? See, J is a function. So J is a function for n to n. So meaning natural number to natural number. So if I input you number one, you should tell me where the one can go, right? Right. So what are the possibility of one can go? One you can go to one, right? Or you can go to two, right? So for example, just now the one that Qi picked one is one going to two. But then you must at least go to one. So that's why we have this inequality here. And J1 actually have to go to at least one. Right? So you can prove this. Let's try and prove this. Okay. So what is the usefulness here? What's the usefulness here? Well, I actually claim that this is done. Maybe you can think about why is it done. Okay, I basically claim that we are done here. Why are we done? Let's think about it. Why are we done? Okay, so you need to go back to assumption, or you can just look at this one. This one, the useless one. Usefulness is this one. This one is the most useful. So you have n greater or equal to n, an minus l will be less than so. But then this jn is already greater or equal to n. So this jn, right, is one of the n here. You understand? 其中一个 n，因为 jn 是一个号码大于，它是一个其中一个 n 单啊小于数。OK， make sense? Make sense? Actually, yeah, if you realize that this is the content of our quiz just now. If you compare 1 over n plus 1 to 1 over n, you remember in the quiz just now, we have 1 over n plus 1. So actually 1 over n plus 1 is what? 1 over 2, 1 over 3, 1 over 4, 1 over 5, and then so on, right? But then this is actually a subsequence of 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on. Okay, if you realize the proof that I write just now, right? I also have this part here. Jn greater or equal to Jn greater or equal to n, which is this part here. Which is this part here. Okay. Okay. And then you see, I pick the same n epsilon rule. It's the same story. Right, so just now I prove it for general. So once you learn the theorem in the class, right, actually to prove this, you don't need to use this hint. You can say that, oh, because it's a subsequence of the sequence that I know where it converges, so I know where one of the n converges, so they have the same. You can put it like that. Okay, otherwise you need to demonstrate this proof. Any question? No question? Okay. Okay, good. So this is one of the facts you need to remember. If one sequence converges, any subsequence must converge to the same limit. Okay. Next. This is a very important thing in analysis, which is called the Bolzano-Weierstrass theorem. Or sometimes they call it a sequential compact theorem. But then Bolzano-Weierstrass is a Nice name to remember. So maybe so I have introduced a few theorems. It's not theorem, but it's an axiom. And Bolzano-Weierstrass. What else? Yeah, I do. More. Yeah, so these person, right? You can go research on them, and then that's the project you can do on them. Okay, but then those projects will focus on their living and then the purpose of the theorem. Okay, instead of the how we use the theorem itself. Okay, so we want to look at a humane part of mathematics and what lead them to this theorem, or what are they used for. Maybe they're using for something else. They have some other goal, and then they suddenly achieve this. Okay. Well, so what is it? So every sequence an in a closed bounded interval CD has a convergent subsequence Bn that converging to a point in CD where C and D is in R and C is less than D. Okay, so what does this mean? So if you have a sequence, again, living inside a closed interval, so how do you draw your closed interval? So let's get out your number line, and then you have CD here. So you have a AN here. So maybe A1, A2, A3, A4, whatever. So it's inside here. It says that this sequence here might not converge, but it will contain a convergent subsequence. You can extract out a subsequence that converge. Understand? Okay. Sequence itself might not converge, but then you can extract a convergent subsequence. Okay. Does this make sense? Injie, can repeat what I said.
That is if that like the sequence can be either converged or diverged, but you can get a subsequence, then it's converged.
Yes, that's right. Very good. Okay, so you have a sequence inside here. It might not converge, okay, but then you can extract a convergent subsequence. Okay, you can take a subsequence of it, then that subsequence. How on earth we're gonna prove this? What time is it? 1:42. Okay, so there are two versions of this proof I want to show you. I want to show what's their construction, but then I think we only have time for one. Let's do one of it first. So there are two main principles we will use. One is pigeonhole. The other one is monotone convergence theorem. Which one you want to see first? Do you know what is pigeonhole? What's pigeonhole, honey? Maybe you can use pigeon and hole. More than one pigeon. Okay. So which one do you want to see first? You want to see monotone convergence theorem, or you want to see pigeonhole? Maybe we get Jingwei, huh? Jingwei to pick. You want pigeonhole or you want monotone convergence? Pigeonhole? Okay, well, let's do pigeonhole. Okay. So let's see how we're going to use pigeonhole to find this convergent subsequence. Good. Okay, so first, so we need to find our hole. So where's our hole? CD is one big hole only, so we need a lot of a hole. Okay, so let's divide the interval CD into two closed bounded subinterval that have equal length. So this is what I mean. So I just found the midpoint between them. Okay, find the midpoint between them. So what does the pigeonhole tells you? Because your sequence is infinitely many of them, right? So what does it mean? So either one of this should contain infinitely many AN. Either one of this. Maybe A1 here, all the rest here, for example. But then either two of them have infinitely many terms, but at least one of them must have infinitely. Does it make sense? Okay. Otherwise, I don't know where to put my infinitely many terms if both of them are finite. Okay. So at least I cannot say both of them because I give you an example, right? One of them just contain A1, then the other contain infinitely of them. So at least one of these should contain ANs of infinitely many N. Okay, N. Okay, at least one of them. Then we will choose it. Okay, we will choose this one to become and call it C1D1. Okay. So what do you think? What are you gonna do next? Split it again. Okay, we'll split it again. Before splitting it, do I need to do something else? Okay, before splitting it, let me see. Okay, so before splitting it, let's pick our subsequence first. So the term in our subsequence. So also we choose the first term of our subsequence B1, okay, which is AJ1, such that AJ1 is living inside here. Okay, so meaning because there are infinitely many terms there, right? Just pick one term out of here, one of the AI out of here. Okay, call it B1. Okay, then what do we do next? So we do exactly what Xiang said just now. So then subdivide again. And so subdivide again so that we get C1D1 becomes C1 up to the midpoint. And then from the midpoint up to D1. Again, Pigeonhole says what? There's at least one of them must contain infinitely many sequence. You cannot use up one because the sequence of infinitely many. You can't use up. Okay, at least one of them should have it. So then you will let C2D2 be one of the half that have infinitely many terms, which has infinitely many terms. Because there are infinitely many terms, right? Then pick another AN from there. Okay, so we take B2 to be one of the AN in there, but then there's a condition you need to satisfy, right? You need to make sure that this J2 here, so we will let, so how to say this? So such that J2 is greater than J1 because we want to keep the increasing property, right? Because depend on what you pick for the J1 behind the J2 that's greater than J. Okay. Does it make sense? Subsequence, we cannot pick the same J1, the same term come up. We need to pick the next one. Okay, next one in the sequence. Okay, such that this term here actually live inside our second infinite subdivided. So continue in this way, what can you imagine here? So you got a CD, right? You got a CD, and then you subdivide, and then maybe you subdivide again, right? So can you see that? What are we doing here? What are we doing here? Nested interval. Okay, we have the nested interval. So the interval is like nested inside. Okay, so let me write down what we have. So continuing in this way, what we have produced is a nested sequence of interval. Okay, we call it CNDN. Okay, what's the length of it? You know what's the length? It's actually 1 over 2 to the power n times d minus c. Okay. Does this length make sense or not? Because d minus c is the total length, and then you halve it, halve it, halve it, halve it, halve it. So this number here, is it clear that this number converges to 0? This length converges to 0. Okay, we have a nested interval and then converge to 0. So what does this mean? By nested interval, there is a x that live in every sub interval here. Okay, so there is by nested interval theorem, there exists a unique x that live in every CNDN. Sorry, I use this notation, shorthand notation. Okay. Right. But then what do we left to show here? Okay. What we left to show here is we think that this candidate is our limit of our subsequence. Okay, we think that this is the limit of a subsequence. So this we're gonna show this. So in fact, we show that x is the limit of our subsequence, Bn. Okay. So how on earth we're gonna do that? Well, let's write out our working basically. So we want to show that absolute value of Bn minus x should be something less than epsilon. Right, something less than. So how are we gonna do this? Well, okay, let me guide you a little bit. So this Bn and x, right, where they live in, they are living in some interval. Okay, what interval they live in should be dn minus cn, right? Okay, between cn and dn. But then what's this length here? This length is 2 to the n of d minus c. Okay, 2 to the n of d minus c. So can you make this number less than epsilon? If you can make this number less than epsilon, then you're done. But then just now we say that this number will converge to 0, right? So that means you must be able to make this less than epsilon. Okay, so how are we gonna do that? Okay, so how are we gonna do that? So let me give you some hack here. Like epsilon greater than 0. We can actually choose epsilon like n epsilon like this. So what I'm gonna choose is n epsilon greater than d minus c over epsilon. Is that right? Yeah, okay, this is right. So why I choose this? Why do I choose this? Why do I choose this? Why do I choose this? Because if I have this, okay, this is by what? This is by what? Why can I choose n epsilon like this? By what property? What property? What theorem? Yes, okay, by Archimedean property, you can choose this natural number that greater than that real number. But then this n epsilon here, I can compare to 2 to the n epsilon. Correct or not? If you don't believe this, you should show this as a lemma. This one is a lemma. Okay. Is it true? If you put 1 here, 2 to the 1 greater than 1, 2 to the 2 is greater than 2 to the 3 greater than 3. So what do you need to prove here? You need to prove by induction actually. Okay, this thing. You can try and prove by induction. Or the other way to see it is 2 to the power is an increasing function also. So if you turn out to know that effect. Okay, so let me ask you, if I have this factor, how do I put it here? If I have this fact, how do I put it here? It's just inverting, right? I invert. Okay. So this will implies that I turn around the n, so such that for all. Okay, let me rewrite here. Such that then for all n greater or equals to n epsilon, okay, we should have 2 to the n greater or equal to 2 to the n epsilon, right? Okay, so 1 over 2 to the n should be less than or equals to 2 to the 1 over 2 to the n epsilon times d minus c. But then this is strictly less than 1 over epsilon times d over c. But then this is less than epsilon over d minus c times d minus c, which is epsilon. Okay, does it make sense? Okay, so this one I use here, this one I use here, and this one I use here. Or maybe let me label it. So here is 1, is 2, is 3. So here I use 1, here I use 2, here I use 3. Okay. Good. Good. Okay. Maybe the hard part is to think about this one. This is a small thing that we need in order to put everything. But then from here, you should kind of guess what is the small thing you need. Okay, from here, you should kind of guess what is the small thing you need. Okay. Any questions? Any questions so far? Then we are done. This is using pigeon hole. So actually, we use this pigeon hole plus the nested interval theorem. Okay, we create a nested sequence of intervals. And that special point there is a limit of. Okay, any question so far? Okay, if no question, next week we will start with this thing, but we are proving it in a different way, monotone conversion. So in that case, we need to produce a monotone sequence of which is bounded. Bounded is clear already, right? Because it's bounded by C and D. But then how to pick a monotone sequence, monotone subsequence. So this is a technique. Yeah. Okay. If no problem, maybe we'll see you on next week for tutorial. This week holiday or Friday holiday? Yeah, Friday is a holiday. Okay, see you next week.